over with. Can everyone hear me at the back there? Very good. Okay. So this is going to be very fast and a very long talk. You know, you're supposed to only say 3 things in a presentation. I'm going to say about 200 things. So I apologize. This is super fast and super quick. So functional design patterns is basically a brain dump of everything I can think of that can squeeze into 60 minutes. So my name's Scott Wlaschin. I have a website, fsharpforfunandprofit.com. And F-Sharp works as a group of people who do F-Sharp consulting. So if you want F-Sharp consulting, come and ask us. Where's my slide thing? Here we go. Of course, my thing is, there we go. So I was a bit hesitant to use the word patterns because obviously there's a lot of overloaded connotations with patterns. So I thought about using practices or approaches or tips or something. But you know what? My thing is not working. I'm going to reluctantly stick with patterns. So these are not gang of 4 patterns. These are just patterns when you do something over and over and you give it a name. It's just kind of replication. So before I get started, I'm just going to give you a little bit about my background because a lot of people think that functional programmers are very anti-OO and they're very academic and they don't really understand OO and they just hate on OO for no reason. So I'm going to give you my background. So as you can tell, I've been around a long time. This is a childhood photo. That's me over there in the corner. That was a vacation that ended badly. So, you know, like most people, I did the usual things, the boring languages like Icon and Modular 2 and Prolog and stuff. But eventually I discovered Smalltalk, which I totally love, and I still love to this very day. I think it's an awesome language, and I think you should all learn Smalltalk if you don't already. So I did Smalltalk for quite a while, and so I was, a very serious Smalltalk guy. And even though I love Smalltalk, even the Smalltalk people hated Enterprise OO, right? So, because that wasn't real OO. Real OO was Smalltalk. So it's very easy to make fun of Enterprise OO. So even though the functional programmer guys make fun of Enterprise OO, the Smalltalk guys also did. And so, it's like shooting fish in a barrel or shooting marine vertebrates in an abstract barrel. Proxy factory. So it's easy to say. Easy for you to say. Okay. So, and then I discovered functional programming a few years ago. And I love functional programming too. And, it started off kind of innocent, and then it got kind of serious, and I started doing quite a lot of it, and I set up a blog and so on. And then one day this guy came and grabbed me. He assimilated me. And that's what happens when you dabble too much in functional programming. You get assimilated into the functional programming community. And they took me to this ivory tower. They didn't take me to the top floor. The top floor was reserved for Haskell programmers. I'm an F-sharp guy, so they put me a bit further down with the OCaml guys. The Visual Basic people are down in the basement. And of course, the Lisp people are like on another planet altogether. So I've escaped from the ivory tower, and I've come to tell you the design patterns that I know about. So, when you're learning a new paradigm, you typically want to transfer the knowledge you have from the old paradigm to the new one. So, we're all familiar with these OO patterns, yada, yada, yada. We've seen them thousands of times before. So how do they translate into a functional model? So what we were told in the ivory tower is we just answer every question with functions, right? So single possibility functional is functions, open-close principle is functions, dependency inversion principle is also functions. Interface segregations, functions, functions. So I guess the point of this slide really is that functional patterns are not the same as OO patterns. They're different, okay? So there's no point trying to transfer OO patterns to functional patterns. I'll give you a couple examples, but you really need to change the way you think about programming to be a good functional programmer. So the kinds of functional patterns that you're probably all familiar with, apomorphisms and zygohistomorphic prepomorphisms. Yeah, no, I'm not going to talk about those things. That's too serious. What I'm really going to talk about is core principles of functional design, which is functions, types, composition. Functions as parameters, which is a really sort of the main thing about functions, using them in a different way than you might do in an object-oriented world. Functions as interfaces and as the sort of way of doing abstraction, partial application, dependency injection, continuations, and the pyramid of doom, monads, especially for error handling and async and things like that, and then maps, a little bit on maps, and finally monoids, which is a very mathematical sounding word, but it actually turns out to be very useful for aggregating data operations. So this talk, like I said, it's going to be a super quick talk. It's like one of those bus tours. You go to a city and you try and see all the tourist attractions in 5 minutes, and you don't really get a chance to stop and look at it properly. That's what this talk's going to be like. So it might be a little bit frustration if you want to know more about things, but at least you've been introduced to the terms, hopefully, and you can go and find out more about them, because there's no way you can understand all this stuff in 60 minutes, even in a day. So don't worry if you don't understand anything. It's really just a whistle-stop tour of all the features, and maybe to demystify it a little bit. So there's a lot of core principles of functional programming, but here's some of my favorites, or rather the ones I can fit into 60 minutes. So I think it's very important to understand the core principles because, again, you try to bring in your existing paradigms if you're an OO programmer, and it's kind of frustrating. You keep saying, how do I do this, how do I do this? If you understand the core principles, it actually makes life a lot easier because you'll not even attempt to do certain things, and you'll do things in a different way if you really understand what's going on. So the core principles of functional programming, or a couple of them, are functions are things, right? They're not just methods on a class. I like to use the railway analogy a lot, so I'd like to think of functions as a little bit of railway track, and there's an input and an output. Composition everywhere. And composition, I mean like Lego. You take 2 bits of Lego and you glue them together, you get another bigger piece of Lego, and you can glue more to that, and you get another bigger piece. So that's composition. And types are not classes. So we think of types and classes in OO as basically the same thing. They're more like set theory. Okay? It's a different way of thinking about types. But it actually turns out to be quite powerful. So let's start with the functions as things. So a function is a standalone thing. It's not attached to a class, not attached to an object. There's a little kind of tunnel on this piece of railway track, and something goes into the tunnel and it comes out changed. It gets transformed. So in this particular case, I have an apple turning into a banana. And to demonstrate that functions are things, this is some F# code here. So I have an assignment to a number, z equals 1. So I put a little 1 in a box and I give it a name, z. Now if I define a function in F#, I define a little bit of railway track and I give it a name add. What's interesting is in F# and in most functional language, the way you define a function and the way you define a value are the same, and that's not a coincidence because functions are just things like numbers, like strings that you can pass around. So that even the way the language syntax works tells you something about how it thinks about functions. So functions can be used as inputs and outputs and parameters. So let me just give you a really quick example of these things. Here's I'm not expecting you to understand the code or read the code, just can look at the pretty pictures. So here's a function that takes an integer and it outputs a new function, okay? So this is it's a function that generates functions as output. This function takes a function as input and returns an integer. And then this other function here takes an integer in, spits an integer out, and it takes another integer, it takes another function as a parameter. So it's parameterizing what it does using a function as a parameter. So this is a function that takes functions. This is really common. It may make your head spin initially if you're not used to functional programming, but once you get your head around it, it actually makes a lot of sense. So the next principle, composition everywhere. So what do I mean by function composition? Here's a thing which takes an apple to a banana. Here's something that turns a banana into a cherry. How can I glue them together? I just glue them together like 2 bits of railway track. Right? And what I have now is I have a new function that turns apples into cherries. Now what's cool about this new function is I don't know how it was built. It's encapsulated how it was built. It's just a function. I don't really care how it works inside. So that's how you kind of get abstraction already. I don't care about how functions work. I can build new functions from smaller functions. So that's a very cool feature about composition. And that leads to the first sort of design paradigm, which is functions all the way down. Sometimes people say functions in the small, objects in the large. I would say functions in the small and functions in the large. You can use functions everywhere, and I'll give you an example. So you start off with a low-level operation like, uppercasing a string. So it has an input and an output. And then you take these low-level operations and combine them into a service, say an address validation service, and it has an input and an output. And notice that it's inputs and outputs, it's not requests and responses. So it's not a request-response model, it's an input-output model. Sounds very similar, but it's actually subtly different when you get into composition. And by the way, for people who don't know what a service is, everyone knows what a microservice is, right? So a service is just like a microservice, but without the micro in front. So yeah, old school. All right, so you take a bunch of services and you build them up into a use case. And a use case is normally event-driven. Some request comes in, and you do something with it, and some response comes out. And then you take a bunch of use cases, and you compose them into, for example, a web application. In this case, the input is a HTTP request, the output is an HTTP response, and inside there you've got all these different use cases, and there's some sort of controller, dispatcher, something that figures out which use case to run based on the input. So the same model of composing smaller functions into bigger ones works at the low level, and also works all the way up to an application. At some point, you might, when you have systems, you have to start using message queues or something to do asynchronous. That's when you start getting rid of the functions. But then that's where reactive functional comes in. So composition is sort of fractal. Fractal may be not the accurate word. Self-similar might be a better word, but fractal sounds cooler, so I'm going to say that. Composition is fractal. It's the same at the small level as the high level, both. All right, types are not classes. So what do I mean by that? So here's a class diagram. But these are not types. These are classes. So don't think about classes when you think about functional programming. So what is a type? Okay. So it's quite a lot of debate about what a type is, from a kind of academic point of view. But I'm going to use this analogy that you have a function which has a bunch of inputs and a bunch of outputs. A type is just the name given to the set of inputs or the set of outputs for that function. Okay. All right. It's just a label. You have a set of things which are valid inputs. That's a type. That's all it is. So, for example, int is a type. Okay. I could have a set of integers. Any of those integers are valid input. That's a type. But it doesn't have to be primitive. It could be things like a customer. So you have a customer object in your domain, and that's an input to some sort of function. So the entire universe of customers are valid inputs. And you can even have functions as inputs, right? So, or outputs. It's just a set of all the int functions. That's a type as well. And we'll be seeing integer function types in a minute. So that's what types are. It's just a name given to a set of values. So one of the things about these kinds of functional types is they don't have any behavior. So let's say we have a function that maps lists to lists. A list is just some data, right? If I want to do something with it, I need another function. So I have functions that transform lists to other lists, or transform lists into integers or strings or whatever. Those are completely different from the lists themselves. The lists have no behavior. So the behavior and the data are completely separate. The thing about types is because they don't have any behavior associated with just data, they can be composed just like functions. So most functional languages have an algebraic type system, which is not an OO type system. So an algebraic type system, you start with primitives and you create new types by gluing them together, just like you compose functions. And there's two basic ways you can glue them together. You can glue them together by multiplying them, which sounds kind of strange. But here, for example, I have a set of people, a set of dates, and I combine them together and I get a birthday. Okay? So that's called a product type. And the alternative way of doing them is to add them together. So if I have a cash method or a check method and a credit card method, I combine them together as a choice. That's a payment method. So that's called a choice type, or a union type, or a sum type. So let's talk about how types fit into a quite important principle, which is totality. So totality is something that functional programmers strive for a lot. So totality just means a function, for every input for a function, there's a valid output. All right, sounds simple enough. So let's look at an example. So here's a very simple example, 12 divided by. It's a kind of toy example. 12 divided by 3 is 4, 12 divided by 2 is 6, 12 divided by 1 is 12, 12 divided by 0 is what? Okay, there is no answer. This is an undetermined and undefined result. So this is not a total function as it stands. So you might say, let me throw an invalid argument exception. Okay, that might be the OO way of doing it. Actually, it's not the OO way of doing it. It's the C# and Java way of doing it. I'm going to throw an exception here. But what happens is I look at the type, and this function says it takes an integer and it spits out an integer, and that type signature is a lie. Okay, it's telling me that it will spit out an int, and that is wrong because it doesn't always spit out an int. Sometimes it throws an exception. So I don't like type signatures that lie to me. Okay. And the thing is, if you're telling me you can handle a 0, you tell me you can handle any integer, and then if I give you a certain integer, you say, sorry, I can't handle it. Well, what's up with that? Can't you can write better code. That's a really stupid way of writing code. So what's the alternative? Well, the first alternative, don't do that, okay? Please don't throw exceptions. The first alternative is to constrain the input. So I'm going to define a new type called non-zero integer. And 0 is not in that set, all right? 0 is missing. Now, if 0 is missing, I don't have to handle it. So that's really nice. So I don't have any problems. This is a total function. Every input has a good output. And if I look at the type signature, it says it takes a non-zero integer and gives me an int. And that is a true type signature. That's not lying to me. And it acts as documentation. It tells me that you better not pass in a 0. In fact, compile a static type language will not let you pass 0 into that function. So you get a compile error if you're trying to pass 0 in, which is kind of nice. Now, the other way of doing it is to extend the output. So you say, OK, you can give me a 0, and I'm just going to turn nothing. I don't know what the answer is. But then in all the other cases, I have to change them to be something. So in cases where I do know what the answer is, I return sum 4, sum 6, sum 12. So now what we do is we have an option of int. Right? So sometimes it's something, and sometimes it's nothing. In which case now int 0 is a valid input, but the output is now optional. Again, if I look at the type signature, it says you give me any int, I might give you an int back. Maybe, if you're lucky, maybe not. But again, the type signature is telling me the truth, and it's acting as documentation for what the type is doing. It's not going to lie and pretend that it's always going to give me an integer back. So total functions are really nice, and this is something that functional programmers do strive for, and the type system is your friend here, because you can define these types like optional int and non-zero int and all these kinds of things. You end up defining all these types to help you define what your functions do. So that leads to the next design principle, which is to use static types for domain modeling and documentation, not just for type checking. You can actually use static types to embed business rules in, which is hard to believe. But it's actually possible to create a situation where things which are illegal in the real world are not compilable in your code. So the types act as a sort of compile time unit test. Now, unfortunately, that only works for static type language, so sorry, Clojure people and JavaScript people. And also, I don't have enough time to talk about it. I actually have a whole hour-long talk on that one topic. If you go to my website, you'll see a video and slides for that. So that's enough of types. Next, functions as parameters. Parameterize all the things. It's the rallying cry of functional programmers. Let me give you a little example. So here we have something that prints a list of integers. And typically as a program, you look at that and you say, you know what, you've hard-coded that number 10 in there. That's kind of yucky. Let's parameterize this and pass in a list. So it's sort of second nature to parameterize the data structures. We don't like seeing hard-coded constants in our code, right? It's just second nature to get rid of them and replace them with parameterized things. But if you're a functional programmer, you say, oh, yuck, you've hard-coded the behavior in there too. Let's parameterize that as well. So a functional program would immediately create a parameter, which is a parameter to do the thing for each item. So now what I do is have two parameters, one which is the list and one which is the action that I'm going to do in each element. And what I've done here is I've completely decoupled the three things. I don't care what kind of list it is, I don't care what kind of action it is. It could be a list of ints, it could be a list of strings, it could be an action that works on strings or anything. So it's infinitely more generic already. And we've decoupled the list iteration code from what I do inside the list. So this is actually more generic. I mean, this will often replace, thousands of methods in an object-oriented thing can be replaced with one method in a functional language. Obviously, it's nice if the language can help you by making it easy to parameterize. If you have to go to a lot of trouble to make function parameters, it's really painful and you don't do it. But if it's really easy like this, I can do it in 2 lines of code. So let's look at a real example. This is a little bit of a C# kind of snippet. Obviously, C# has link, when I show these examples, C# people say, well, yeah, I can do this with LINQ in one line. It's like, yes, you can. It's called functional programming. But I'm going to use traditional style for it. Let's pretend this is C or something, okay. So you have a loop and you say, okay, there's duplicate code here. Don't repeat yourself. We know that this is bad. How can we get rid of this duplicate code? Well, what we do is we look at what's in common between the two functions and what's distinct between the two, what's unique about the two functions. So what's in common is this loop. What's distinct is that in one of them you set it to the initial value as 1, in the other one the initial value is 0. And then also the action that you take each time through the loop is different in both cases. So we need to preserve the distinctions and get rid of the common boilerplate code. And in F#, that's called list fold. And that does the looping for you, and all you have to do is pass in the initial value and the action that you want to take. And what's nice about this is it helps you focus much more on what you're actually trying to do with your code. You're focusing on why is a product different from a sum. The two lines really help you understand the difference, and you're not bogged down with all this loop code. So actually LINQ has the thing, LINQ aggregate is the same thing in C#. It's not often used, I think, because it's quite complicated to understand. There's the common code, there's the initial value, and there's the parameterized action. And of course, any decent collection library will have thousands of these kinds of things. There's fold, there's map, there's reduce, there's collect, there's select and pick and choose. And it's worth taking the time to understand the library that your language has, because there's probably a lot of powerful stuff. You can reduce a lot of your code probably down to 1 or 2 lines using these collection classes, collection functions. All right, function types are interfaces. So what do I mean by that? I mean that the function types provide the abstraction layer. So in object-oriented programming, you tend to use interfaces to force you to program to the interface, don't program to the implementation. In functional programming, you program to the function type, right? Not to the implementation. So let's see how that works. So here's an interface, an OO-style interface called a bunch of stuff. It's got 3 different methods in it. If we take the single responsibility principle, which says, only one reason to change, the interface segregation principle, don't contaminate interfaces with too many things. If you take that to the extreme, what do you get? You get a rule that every interface should only have one method. If it only has one method, it's only got I guarantee it's only got one reason to change, and I guarantee you're not contaminating your interfaces with other interfaces. So if you have that as a rule, and you get rid of those 2 methods, now your interfaces look like this. So all your interfaces have exactly one method in it. Now, what's interesting about that is an interface with one method is basically a function type, okay? So do something, takes an integer, spits out an integer. That's exactly, I could have rewritten this in F# as a type called bunch of stuff. It takes an int and returns an int. So any function which takes an int and returns is compatible with this interface. So add 2 is compatible, and times 3, they're both compatible. And I didn't have to say they inherit from this interface, all right? They're automatically compatible by the very fact that they take an int and return an int. So the strategy pattern in OO, you have to pass in a strategy object in a constructor or something, and then you have to do it, assign it to a local field, and then use it, and so on and so forth. In functional model, you just pass in a function. So the strategy is just a function that you call. So I'll try and do it in pictures, see if that helps. There's my strategy in pink. That's my strategy pattern, and I pass it into my main function as a sort of slot there for it. And the nice thing about the functional model, again, you don't have to predefine any interfaces at all. I didn't really have to define an I bunch of stuff type in F# because int to int is a sort of built-in type. I don't need to define it. Anything that's an int to int works. So it's very good for doing things after the fact. I can say I have something that takes a customer to a customer name or something. It's like, oh yeah, actually I want to use another function that has exactly the same interface, and I can just plug it in. I don't have to proactively define all these interfaces all the time. Let's have a quick look at the decorator pattern. So here's an is-even function, and what I want to do is I want to decorate it with a logger function. So again, it's got the same input, the same output, but it's going to print the input, and then it's going to print the output, and then it's going to call the actual internal function. Okay, so it's a decorated version of is-even. And again, because it's an int to bool function, it can substitute anywhere that I had the original function. That's not a problem. But you know what? In practice, a functional programmer probably wouldn't write it like that. It's a little bit clunky. a functional program will probably use function composition like this. So I've got my isEven function. I stick something in front of it. I stick something behind it. I compose them together. And now I have a new function that has the same thing. It takes an int and spits out a bool. This new function is also a decorated version of isEven. And again, I can substitute it anywhere that I had the original function. All right, so there's a problem with all these patterns that we've seen so far, which is, unfortunately, they only work with functions that have one parameter. So, because I have to have this connecting inputs and outputs. So that's a shame. The good news is that every function is a one-parameter function. So all these patterns actually work for every single function, which is kind of nice. So in functional programming, you don't really have two-parameter functions and three-parameter functions and one parameter. Every function is a one-parameter function. Let me give you an example. So here's add, that you might define it in a normal way. It's got two parameters. But you can also define add in another way, which is, an add is just a value, it's just a thing that returns a lambda. All right? So the add itself now has no parameters, but it returns a little bit of railway track that has exactly the same behavior as the function that has two parameters. So there's add defined as a zero-parameter function in a sense. And of course, if you can do a two-parameter one and a zero-parameter one, why can't you do a one-parameter one? And in this case, I take one parameter and I return a lambda that has that first parameter baked in. So it's a function that takes a parameter, spits out a new function that has that parameter baked into it, and now I have yet another function. So it's a function that generates functions. So in a true functional language, every function, every multi-argument function is actually a function that generates other functions all the way down until you've passed the last argument in. So here's a concrete example. Here's 3 equals 1 plus 2. It's pretty obvious. In F#, you can actually take that plus and move it to front, and it becomes a little function like that. So it's a two-parameter function. But then what I'm going to do is I'm going to take the plus 1, I'm going to pull it out, I'm going to copy and paste it, and give it a name. I'm going to call it add1. And at this point you say, yeah, but now it's missing a parameter. And I reply to you that it's actually not missing a parameter. Add is a one-parameter function. Okay? You might think that addition is a two-parameter function, but no, it's a one-parameter function. You can try this at home and see for yourself. So once I have my add1, I can then pass the 2 to it, and I can get my 3 as I did the first time. So this is true for any function can be broken down this way into one-parameter functions, and you can always pass in an argument and bake in the argument. So that leads to a really powerful technique called partial application, probably one of the most important patterns in functional languages. So let me give you another example. Here's printing my name, and I have a function here. Print has 2 parameters. The first parameter is a format string, and the second parameter is my name. And what I'm going to do is I'm going to put the parentheses around the first 2 bits. This is one of the reasons why functional languages tend not to have parentheses. They use spaces between the parameters. And the reason is you can do exactly this thing. You can put parentheses around the front bit. Okay, you can't do that in C# or Java. So you can actually take that front bit and turn it into a one-parameter function, which I'm going to call hello. So hello is now a one-parameter function that's just missing the name part. And then I can call it with my name in the usual way. But it's a one-parameter function. And now I can actually use this hello function I've defined all over the place. So originally I had a kind of hard-coded version that only worked in my context. But by partially applying something, I've now got a kind of reusable function that I can pass around, and other people can use it as well. So that, it's very common, for example, when you're using lists, that you use partial application. So there's my partially applied hello function. And there's a list of names, and for each name in the list, I'm going to iterate over it and call this hello function. So the missing parameter that hello needed is going to be supplied each time I loop through the list. Here's another example. I'm going to partially apply 1 to get an add1 function, and I'm going to partially apply 2 to get an equals 2 function. Okay? So both of these the add1 and the equals 2 are missing a parameter, but when I apply them to a list, then the extra parameter is provided by the list iteration routine. So 1 to 100 list map, add 1, that adds 1 to each element in the list. Filter equals 2, it filters on the equality function. So you can see that it's really nice to build up little kind of utilities, little helper functions, just one-liners, and then your code looks quite nice. This code is very readable. Add 1 to everything in the list, and then filter it where it equals 2. Very, very readable. So it's kind of self-documenting code. Partial application for dependency injection. This is a really important one. People say, how do you do dependency injection? Because I know how to do that in OO, and I need to do it in function, and I don't understand how to do it in functions. So let me show you. Let's say you have a repository, and this is the repository interface, where you give it a customer ID, and it loads a customer from the database. Now, this is not really a repository interface because it's just a type, and in fact, I don't even need to define this, and everything would still work. But this is the equivalent of having a get customer repository, for example. So there's nothing in this type that says it comes from a database, right? It's ignorant of the persistence mechanism. So let's say I have a real function that gets a customer from database. Now, this particular real function needs a connection, okay? It's a SQL database. I pass it a connection, and I also pass it a customer ID, and then it does a select on that customer ID. So unfortunately, that function requires a connection, which means that function, as it stands, does not meet that interface. Right? There's a problem. I can't use this get customer from database function where I want to. However, if I take the connection and I partially apply it, I get a new function, which I'm going to call get customer 1. And if I look at what get customer 1 is, get customer 1 now has the type of give me an ID and I'll give you back a customer. So this new customer, get customer 1, does conform to the interface. It conforms to the type that I need. So that's really nice. So now I've abstracted out the fact this is a database function. I can take this function, I can pass it to anybody who needs a repository. So let me show you another example which isn't a database one. So here's the type here. Let's say it's an in-memory database. So instead of having a physical database, I'm going to have a dictionary. And again, I have a particular method that works with the dictionary, but the dictionary is now the first parameter, and I want to get rid of that dictionary. So what I do is I partially apply it, and I get a new function, get customer 2. And get customer 2, the dictionary is already baked in, and all it needs now is the missing parameter is now just the customer ID. And again, it conforms to the type that I need, the interface that I need. And so the get customer 1 is a database function, get customer 2 is an in-memory function. They both have exactly the same type. They both kind of conform to the same interface. I can pass them around. They're completely interchangeable. That's how you do dependency injection. So the Hollywood principle, don't call us, we'll call you, otherwise known as continuations in the functional world. So let's look at this divide function. Obviously, if it's 0, it's going to throw an exception, right? So the problem is that I don't want it to throw an exception, okay? The problem is the method has decided to throw an exception without asking me, right? Who put the method in charge of the universe? It's like, I don't want you to throw an exception, but you're going to throw an exception anyway. I want to be in charge, right? So the way to make me in charge is for me to pass in functions that do what I want on each case. So if it's 0, I'm going to call this 0 function, and if it's a success, I'm going to call this success function. And that way I have complete control over what this function does. It's not throwing an exception that I immediately have to catch again. It might be that I want to, I might be doing this all the time, I have to it's going to throw an exception, I have to catch it. It's going to throw one, it's catch it. It's like, if I do this, it's never going to throw an exception. I don't have to catch it. It's great. I know exactly what it's going to do. So a continuation is just a fancy word for what happens next. I'm passing in a function that tells the called function what to do next, the very last thing you need to do. So here's the F# equivalent. Again, there's 4 parameters, and there's 0 and success. So 4 parameters is a lot, right? I mean, you're pushing it. And it'd be really annoying if I have to pass. I mean, it's nice and flexible, right? You can see it's good, but I really don't want to be passing 4 parameters every time I call a divide. It's just ridiculous, right? So it'd be really nice if there was some way of kind of baking in the 2 parameters that do the behavior, right? And then I would just have a normal divide function after that. So that's exactly where the partial application comes in, because I've already shown you how to do that. So if we take this function F#, what I can do is define 2 behaviors. If it's bad, if it's 0, I'm going to print bad. If it's not 0, I'm going to print good. All right, that's one set of behavior. And then I'm going to partially apply just those two parameters, leaving the other two parameters alone. And now I have a divide function which has two parameters. It's a two-parameter divide function. It looks just like the original divide function. So I can use it everywhere that I was using divide, except I can completely control what happens. Let's say I don't want to print something. Let's say I want to say, if it's 0, do nothing, return none, and if it's success, return some. So there's how I do that. I bake those in, and then I get a divide function that works like normal for anybody else. And let's say I want to reproduce the original behavior. So I want to throw an exception if it's 0, and if it's successful, I just leave it alone. So there's my setup. Again, I bake the parameters in with partial application, and again, I've got a new divide function that looks just like any other divide function. So this kind of passing in continuations is a really, really powerful technique. It gives you complete control, and if you have a nice functional library, it will allow you to do that. All right? It will tend not to hard code things like, I'm going to throw an exception. It's like, no, you tell me what to do when something bad happens, and then you have control over what happens. So one way you see continuations used a lot in this sense is when you're doing callbacks. So I'll give you an example here. This is a null testing example. If it's not null, do something. If it's not null, then do something else. If it's still not null, do a third thing. These kind of nested null checks are very annoying, and people call this the pyramid of doom because you end up with a super deep nested code. You can do early returns in F# you actually can't do an early return, but even if you could, just bear with me for a second because it's not always applicable. Because you can't do early returns for this kind of thing, like tasks finishing. So this is the same kind of thing. When this task is finished, call this other thing, and when that one's finished, call this other thing, when that one's finished, call this other thing. Again, you get these nested callbacks, you get this level of indentation creeping up, and you get the pyramid of doom. So you see that in all languages where there's some kind of callback mechanism, especially for async or promises or those kind of things, you end up getting this a lot. So it's really ugly. So let's see what we can do about it. So we look at this code and we look at it and we say, you know what, null's a really bad code smell. We're going to replace null with option. Okay, that's much better. There you go. Isn't that much nicer code? No, of course, it's still really ugly code. It's a terrible way of doing things. So turning it to option doesn't solve anything. What we need to do is look at this pattern. There's a pattern here we can exploit, and we can use that pattern to make our code simpler. So this is the pattern. If it's something, do something, otherwise skip it. If it's something, do something, otherwise skip it. If it's something, do something, otherwise skip it, right? That's the pattern. So let me zoom in on that little piece, and if you look at that, it's like that's just calling out to be parameterized, right? Parameterize all the things. So I'm going to write a little helper function called if something do, and if the value is valid, then I'm going to call the function, and if the value is not valid for some reason, I'm not going to call the function. So that's parameterizing all the things, and there's my little function that I'm going to be passing in, and that's a continuation right there. That means keep going if the value is valid, otherwise bypass it. So with that little helper function, I can rewrite my code like this. If something, do something, and if it's still something, do the next thing, and if it's still something, do the next thing. So the code is much, much nicer when you use this kind of continuation-based design. Much cleaner. And that takes us on to monads. So monads is one of those really scary words that you hear a lot of in functional programming. For the purposes of this talk, I'm just going to say that monads is really just chaining continuations together. So it's not really what a monad is. It's a bit more complicated than that. But for the, I'm not going to get into too much, but you can think of it as just chaining continuations. So let's look at how we just did what we did from a kind of monad point of view. So I like to, the good analogy I like is points in a railway track. We've been talking about little functions as railway tracks. So this is a function which is, it has one thing coming in, but two things coming out. So it's either points or, if you're American, it's a switch. So in this case, input, and then if it works, we're on the green track, and if it doesn't work, we're on the red track. The problem is we have a lot of these functions where each one something comes in and it might or might not work. So the way we connect them is if the first thing works, we connect it to the second thing, and if the first thing doesn't work, we just bypass the whole thing. Right? I think that makes sense. It's obvious how you connect them together. And when you have a bunch of them like this, you end up with something like that. Okay? So you just convert, those little things into that. I think that's pretty obvious. That's how you would do it if you had a toy train set. So here's the problem. If I have one-track functions with one input and one output, they're really easy to glue together. And if I have two-track functions with two inputs and two outputs, they're also easy to glue together. I just connect the track up. But what we've got here is we've got one-track input and two-track output. Okay? That cannot be connected together. So what we need is a way to combine these mismatched functions. Okay? So if you talk to a functional programmer and you say, how do you do this? They say bind. Bind is the answer. Bind all the things. It's like a secret handshake. If you go up to someone and say bind, they'll say, yeah, nudge, nudge, wink, wink, you know. FPs, people get excited by bind. You can read into that what you will. Right, so bind is the answer to everything. And what does bind mean? So here's our function that doesn't work. If we can turn it into a two-track function, it does work. So bind is just a kind of an adapter block. Okay, I have a function which doesn't fit, and I want to turn it into something that does fit. It's like a little kind of thing that fits on top of something, and I slot my points or my switch in, and it turns into a two-track function. So that's all that bind is. Okay, if it's a successful input, it calls the continuation, and if it's unsuccessful input, it just keeps going. So that's all that bind is. It's not a mysterious thing. It's just a way of gluing these switches or points together. So let's look at bind for chaining options together. So we saw this before. Here's option bind. So if it's something, you call the function, otherwise you say nothing. So here's the Pyramid of Doom version, and then this is the same version after using bind. Much nicer. No pyramids, linear code, and monadic bind. That's the buzzword. And you can just say to someone, I understand monadic bind, and you'll get into the secret society. Tasks, the same kind of thing. So a task, you wait for something, and if it completes, then you call the next thing, and if it doesn't complete or something goes wrong, you bypass it. And so you can chain tasks together the same way. So we can create a task bind. In this case, it's like when finished, call this continuation. Promises, futures, all variants of the same thing. So here's the Pyramid of Doom version. And here's the same version using task bind, or whatever you want to call it. And in F#, there's a thing called async, which is a really nice version of this. It has all sorts of other nice features like cancellation tokens and all sorts of cool stuff. But this is like the one-liner. You can write this yourself. Right? This will work for like .NET standard C# style tasks. And then finally, you can use bind to chain error handlers together. So let's say you have a function that's going to receive a request and update database and then send out some email to somebody. Very simple function. The problem is, as soon as you start dealing with real world, you start getting all these errors. You have to trap database exceptions, and what if the customer's not found, and what if the server's not available, and blah, blah, blah. And you end up with your code having thousands of error handling routines in it, which are not really part of the main code. Your code starts getting really ugly really fast. I'm sure you've all seen this. And in this case, we've got 6 clean lines that's turned to 18 ugly lines, 200% extra code just for error handling. So it'd be nice if you didn't have to do that. So again, monads to the rescue. We define something that's a success or failure. It's a little switch. There's an example. If the name is blank, it's a failure. If the email is blank, it's a failure. Otherwise, it's successful. You take all the little things and you glue them together into a single 2-track lane like that. And that's what I call the 2-track model of error handling, otherwise known as railway-oriented programming. And I'm going to be doing a talk on this this Friday. I'll come to that in a second. So let's look at what the before code was. Before, we had kind of a linear set of doing something, then do something else, then do something else, then do something else. But it didn't do any error handling, right? If something went wrong, it would just like crash. So let's look at the code after error handling has been added. So with error handling, this is what the code looks like. Okay, it looks exactly the same, right? So the code looks like it's doing the same thing, but in fact, behind the scenes, it's doing the error handling. But it's doing the error handling in such a way that it's nice. It doesn't interfere with what you think that It doesn't complicate your code. It's still quite easy to understand. So I'm talking about this on Friday, or you can go to my website at ROP at F# for Fun and Profit. Maps. Okay, So I'm sorry I'm going really, really fast. Like I said, this is just a super, super fast tour, and I thought I'd just like do a brain dump. So I just want to talk about everything really quickly. Maps now. Okay, so we have a world of normal things, integers and strings and booleans and all this stuff. There's a parallel universe out there. In this case, it's the world of options. So everything in the world down here, an int like 42, there's a corresponding value in the universe of options. So sum 42, and there's a string hello, and in the universe up there, it's sum hello, right? So there's a parallel universe. And what you find you do as a functional programmer is you end up kind of visiting this universe. Like you have something and it becomes a sum, it becomes an option, int option. And then you now need to like do something like add 42 to it or something, and you have to come back down to the world of normal values, and then you go back up to the world of options again, and then you come back down to the world of normal values, and then up and down and so on. So you know, it's just kind of annoying. You have to write a lot of ugly code for this, and you might think, well, how else can you do it? Well, if you're doing it this way, you're doing it wrong. This is actually the wrong way to do it, okay? What you really want to be doing is going up. Once you go up to the world of this alternative universe up there, you want to stay up there, okay? You want to live in the world of options as long as you can, and maybe you have to come down at the very end, right? But you really try to avoid coming back down to the lower world if you can. Once you're up there, it's nice to stay up there. And that's the right way of doing it. That's the idiomatic way of doing it in functional programming. So let me give you an example. Here's a function that adds 42, my favorite number, and this works on normal values. And here's kind of the ugly code, right? If it's something, then I'm going to add 42 to it, and then I'm going to wrap it back up again. So I'm unwrapping the thing, I'm going to apply the add 42 function, and I'm going to wrap it back up again and stick it back into the world of options. And like I say, that's the wrong way to do it. And here's the kind of diagrammatic way. I unwrap it, I do my thing, and I wrap it back up, okay? So don't do it that way. How should you do it? What you want to do is you want to have your add 42 somehow teleported into the universe of options, and you can just use it up there without having to come down. How do you do that? The answer is something called map. So let's say you have a function that takes something to something else in the world of normal things. What you do with map is it will take your function and it will turn it into something that works in options. So, you know, you have an int to string down here, it will turn it into an option string. Or you have a customer to a customer ID, it will turn it into an option customer to an option customer ID. So that's what map does, that's all it does. But it allows you to, once you understand what map does, it allows you to stay in the world of options. So if I have add 42 and I run map on it, I get a new function called add 42 to option, say. So if I pass in 1 to add 42 and I get 43, if I pass in sum 1, an optional 1, I get sum 43 out. I get an optional 43. So here's how it looks in code. I have my add 42 function, I do option map, and I get my new add 42 to option, and so on. In practice, that's definitely the right way to do it, but in practice you don't even bother creating an intermediate function like that. You just call that option map and add 42 straight away. It's like you don't normally go to the extra effort. So that's how you live in the world of options. And the same thing applies to the world of lists. So you have a function that works in the normal things, and there's a whole parallel universe of lists, and you use list map. Any function that works on normal things can be turned into a function that works on lists. And here's an example. I do add 42, and this time I'm using list map. So I'm turning it into a function that works, you know, that adds 42 to every single item in the list. And you might have a world of, you know, async functions or any other, you know, you name it. Any kind of generic wrapped function should have a map type that you can use. So most wrapped generic types, lists and options and monads and all this stuff, they always have a map, and you should really use it. And if you do create your own type, do create a map for it so that other people can use it. And if you hear the word functor, a functor is just a fancy name for a type that has a map. It's a mappable type. That's all a functor is. All right, monoids. So we're getting a bit mathy now, but hopefully you can see these are, even though these are sort of mathematical words, and the mathematicians sort of got there first, unfortunately. So all of the jargon is kind of mathematical jargon, monads and whatnot. But the concepts are actually quite useful to a programmer. So this last concept sounds very mathematical, but I hope you'll see that it's actually quite useful. So let's talk about them. So yes, there is some nasty mathematics ahead. I hope you're not scared of mathematics. You know, if anyone faints, I can call, medical people. So ready for some serious maths? Here we go. 1 plus 2 equals 3, okay? Is that too scary? You can handle that all right? How about the next one? 1 plus 2 plus 3 is the same as 1 plus 2 plus 3. All right, I know that's pretty intense. How about 1 plus 0 is the same as 0 plus 1, and they're both equal to 1. All right. Can you handle that? Pulse rate's not too high? Right. Okay, so what are math... Huh? What did he say? Oh. Yeah, it's not true in JavaScript. Yes, fair enough. Okay. So thinking like a mathematician. So mathematicians, what they like to do is they like to do patterns generation. So mathematicians will look at that and say, there's some interesting patterns here. Let me see what I can come up with. So a mathematician would look at 1 plus 2 equals 3 and say, there's a bunch of things, there's two things, and we've got some way of combining them together, and we make a new thing, which is the same kind of thing as the two things I combined. That's interesting. I wonder if that works for other things too. Let me try multiplication. Does that work for multiplication? Two things, a way of combining them, and I get a new thing of the same type. Well, that's very cool. What about strings? If I take two strings and I concatenate them, I get a new string. Awesome. And if I take two lists and I concatenate them, I get another list. So that's actually really a more generic pattern than I thought when I just thought about using integers. So why is that a useful pattern? So if I look at 1 plus 2, 1 plus 2 is another thing. It's 3, it's another integer, right? And because it's another integer, I can do another pairwise addition on it. And that's another integer, so I can do another pairwise addition on it. And I can keep going and going and going as long as I like. So what I've really done is I've taken pairwise operation and transformed it into an operation that works on lists. So that's very cool. If you have this property, you get this property for free, that you've started with something that just works on two things, and now you've extended it into something that works on infinite lists. Okay, what about the next one? What this really says is the order of combining doesn't matter. I can add 2 and 3 first, or I can add 1 and 2 first. It doesn't really matter, right? Get the same thing. So if I have 1 plus 2 plus 3 plus 4, I can do 1 plus 2, and then I can do 3 plus 4, and I can add the answers, or I can do 1 plus 2, and then I can add 3, and then I can add 4. Whichever way I do it, I get the same answer, right? Well, that's kind of obvious. It's not always true. Subtraction, it doesn't work for. So it works for addition, it works for multiplication, and it works for list concat and string concat and so on. Okay, last one. So a mathematician would say, that's very interesting. There's something, a very special thing, that when I add it, when I use the combination thing to any normal thing, I get the original thing back as if nothing happened. Right? This 0 means that like nothing happened. It's like almost like it doesn't exist. Right? It's a null op, to use programming jargon. And of course, if I'm using multiplication, there's another thing which does nothing, which in this case is 1. If I'm doing string concatenation, there's a special thing that does nothing, which is the empty string. And for list concatenation, it's the empty list, and so on. So that 0 concept is also quite extendable. So let's look at all these generalizations we've made. We started off with a couple of very simple arithmetic things, but we can make a generalization. You start with a bunch of things. There's some way combining them 2 at a time. We have a couple of rules. If you combine 2 things, you always get another one of those things. If you combine more than 2 things, which order you do it in doesn't make any difference. And finally, there's some sort of identity element that doesn't do anything. So if you have these rules, you have a monoid. Okay, so a monoid is very simple. A monoid is anything that just satisfies these 3 rules. So, okay, that's the mathematical thing, but why is that useful to a programmer? Okay, it's kind of theoretical. Well, let's look at closure, for example. As I said, you can take any pairwise operation and turn it into an operation that works on lists, and that is normally called reduce. So list reduce with plus collapses a whole list of integers. If I do it with multiplication, again I can do list reduce with multiplication, and it collapses the list using multiplication. And string concatenation, the same thing. There's my pairwise operator, and if I use it with list reduce, I collapse all the strings into a single string. Very powerful. What about associativity? So because it doesn't matter which order I do things, I can use all sorts of cool algorithms like divide and conquer algorithms, parallelization, incremental accumulation, and so on. So let's talk about the parallelization for a second. So if I got 1 plus 2 plus 3 plus 4, I can do 1 plus 2 on one core, and I can do 3 plus 4 on another core, and then combine the result. Right? So anything where you have this associativity property, you can actually get parallelization for free. Okay, you can split the task among multiple CPUs or multiple cores, do all the work in multiple things, and then combine the results, because it doesn't matter which order you do the calculations in. So that's a very powerful thing. You get that for free if you have a monoid. The other nice thing you get is incremental accumulation. So even if you're not doing parallel stuff, this incremental stuff is quite useful. So let's say you tell me to calculate 1 plus 2 plus 3. And it's like, okay, that's 6. And then tomorrow, you say, you know, I've got a new requirement. I need you to add 4 as well. And you say, oh, no, I have to start all the way from the beginning. I have to do 1 plus 2 plus 3 plus 4. No, you don't have to do that, right? You've already calculated 6. You can just add 4 to what you did yesterday, right? You don't have to start from scratch every single time a new number comes in. So this incremental accumulation is a really nice feature of monoids. And we'll have a look at that in a second. So, and then finally, the entity element's really nice, because if I have an empty list, I can't do reduce, so I need something. If I have a divide and conquer algorithm, there's nothing to divide, I need something. And if there's an incremental algorithm and I've got no data, I need something. So that's where the 0 comes in. So that's where the identity element is useful. Some sort of initial value for empty or missing data. And you don't always have to have an identity element. If you don't have an identity element, it's called a semigroup, another bit of mathematical jargon. There is a way of turning a semigroup into monoid, but I'm not going to go into that right now. All right. So here's a real useful pattern for something you might actually need. So let's say I have an e-commerce site, and I have a bunch of order lines with a quantity and a total, and I want to add them all up. So you might say, well, let me just loop over all the order lines and add up all the quantities and add up all the totals. So what? Yeah, that would work. But I'm going to say, well, you know, I'm clever. I know this is a monoid. How do I know it's a monoid? Because every combination of monoids is another monoid. Because integers are monoids and because floats are monoids, then my order line is also going to be a monoid. So all I need to do is define a pairwise action. I'm going to add 2 lines together. And all I do that is add the 2 components together and create a new one. That's easy. Once I've got a pairwise operation, I can use list reduce, and I get my totalizing function for free. Okay? It's very nice. I get free functionality. I'm always a big fan of free functionality. Plus, if I have a very large number of order lines, I can do it in parallel. Hopefully I don't have an e-commerce site which has like 1 million items in your basket, but if you did have something like that, you could parallelize the addition process. So, here's a common pattern. You have a non-monoid and you want to turn it into a monoid. So you have a bunch of customers, say, and there's data about each customer, how many times they visited your site, how much money they've spent, all that kind of stuff. You want to add all that stuff up, but you can't add customers together because customers aren't a monoid. So what you need to do is you need to turn them into something that is a monoid, in this case something like customer stats, where everything in a customer stat is an integer or some sort of numeric field, right? And then you can add them up really nicely. So that's a monoid. You know that's going to work. So what you need to do is map each customer into a customer stats. And once you've mapped them into the customer stats, you can then reduce them into a total stats. Okay? So there's a map followed by reduce. Okay, so you might have heard of that. So this is a very simplified version of like map reduce that Google has. Obviously the devil's in the details, but this is this kind of same principle, but the simplified version. And someone posted a nice tweet a while ago called "How do you make me a sandwich?" And in this example, you know, a loaf of bread cannot and an onion cannot be combined into a sandwich directly. They're not monoids. But if you slice the loaf of bread and you slice the onion and you slice the lettuce or whatever, the slices can be combined into a sandwich. So the first thing you do is you map everything into the various slices, and then once you've got the slices, you can aggregate them or reduce them into the sandwich. So I think that's you know, a nice model of how MapReduce works. Here's another thing you might see frequently, which is expensive monoids and to cheap monoids. So let's say I have a log file, and I've got a website, and I do all my statistics. I want to get the statistics for the whole week. So I say, oh, strings, the log file is just a string, and the string's a monoid, so I can combine all my log files into one ginormous log file, and then run my statistics program on that ginormous log file. But that's really obviously a stupid idea, right? What would be much more sensible is to take a summary of each day, get the statistics for each day, and add those up. You don't have to create a giant log file with gigabytes of data and run it. All you have to do is incrementally do the day's statistics and then add those up. So what we have is one monoid, which is really hard to work with, another monoid, which is much easier to work with. You map from one monoid to another monoid, which is much more efficient, and that is called a monoid homomorphism. Okay, so that's another buzzword that you might see. Just a few more things. I'm sorry I'm going to run a little bit late. If anyone needs to leave, feel free. Once you start using monoids, you start seeing them everywhere. So if you do any kind of DevOps and you have to have metrics, you've probably heard this guideline, use counters rather than rates because counters are much easier to accumulate. You can actually rephrase that as make sure your metrics are monoids, okay? Because they aggregate, they handle incremental stuff, they can handle missing data. So monoids are a really useful concept. We've been talking about monoids with data, but monoids actually work with functions as well. So let's look at some functions. Here's two functions, and I'm going to glue them together to make a third function. The problem is this new function is not the same type as the original functions. So it doesn't even satisfy the closure requirement, right? So it's not a monoid, which is a shame. However, if I have a function that takes apples to apples, and I combine it with another function that takes apples to apples, I get a new function that takes apples to apples, right? So that is closed, right? It's a new kind of function, but it's the same type as all the other functions. And the associativity you get from function composition, it turns out that functions like this are monoids, right? So this is a special kind of function where the input type is the same as the output type, all right? So functions where the input type and the output type are the same are monoids. So what should we call these kinds of functions? How about calling them functions with the same type as input and output? No, we're not going to call that. We're going to call them endomorphisms. And the reason we call them endomorphisms is because, again, the mathematicians got there first and they already gave them a name. We probably should use the same name that they use. So all endomorphisms are monoids. So here's some simple endomorphisms. Plus 1 is an endomorphism int int, times 2 int int, subtract 42 is int int. They're all endomorphisms. It means I can reduce them, and I get a new function called plus 1, then times 2, then subtract 42. Obviously, it's kind of useless function, but it just goes to show that I can actually create new functions from other functions. Let me show you a more practical example with event sourcing. So if you're doing event sourcing, how many people do here do event sourcing? A lot of people, yeah? So with event sourcing, you have this thing, an event application function, that you start with an event and you have an old state, and after you've applied this event to it, you've got a new state, right? So that's what the function looks like. That state to state is an endomorphism. So any function that contains an endomorphism in its signature can also be converted into a monoid. So let me give you an example of that. So I have a bunch of events. Apply event 1. I'm partially applying the first event because I want to get rid of that event, and I'm left with a state-to-state function, which is an endomorphism. And I partially apply the second event, and I partially apply the third event, and now I have a bunch of state-to-state endomorphisms. I can run reduce, and I get one giant function, which I'm going to call apply all events at once. All right, so there's something practical. I can actually combine my event applications to make new event application and new functions that do stuff. And of course, this is parallel. So I can do, if I have, there's something where you may well have 1 million of events and you want to aggregate them nicely. This will allow you to do parallelization of that. And it can handle incremental updates, and it can handle missing events. So finally, monads versus monoids. Okay, two very bizarre sounding things. Hopefully they're not quite as scary as they might have been at the beginning of the talk. Is there any relation? They both have mon at the beginning. Okay, is there any relation between them? There is. So here's our monads, our railway tracks. And if you combine two of them together, you get another one. So they're closed. And the order you combine them in is not that important. So they're actually associative. And there actually turns out there is an identity for monads as well. So monads are actually monoids. And some monads can also be added together in parallel, and again, you get a new one, and the order's not important, and these are monoids as well. So there's something called the monad laws, which you might have heard of. So the monad laws are really just the monoid laws in disguise. So you have closure, associativity, identity, and so on. And people say, well, what happens if you break the monad laws? You know, that's a common question. Well, the answer is, of course, you go to jail. But in addition to that, you lose the monoid benefits, such as aggregation. So I'm just going to give you this. I'm not going to tell you what it means, but a monad is just a monoid in the category of endofunctors. Okay, people hear this all the time. Hopefully your head won't explode too much. All right, I'll leave you with that. Thanks very much.